Hey Males, here we are with topic 2 in the math review section of integrated 2, and we're going to be looking a little bit at graph setup and calculating slopes. Now I'm not looking for hard and fast rules here, but I'll tell you one pet peeve that I have. Let's say I give this student this graph paper and they pick some scale, and on their scale they plot their data and it's that big. If I've given you this whole sheet of paper and it's that small, it's going to be really hard. Your data is going to be so compressed, this line's not going to show maybe some of the subtle changes in the data there, and it's just not making good use of it when you can zoom it out. I mean, come on, I know you guys have better young eyes than I do, but we would all be taking our screen and zooming in on that, not wanting to see that as just some tiny corner. So until paper, we can do that just with paper in class. We're going to try and pick some scales that take best use of the amount of space that I've given to you. So let's look at guidelines for picking appropriate scales. And these 3 steps aren't hard and fast rules by any sense. If you pick this scale of 5 and I think you could have gotten by with 2, that's going to be okay because you're still going to use the majority of your data. If you pick a scale of 25 or 50 and I think you could have gotten by with 2, then that is going to be a problem because that's going to shrink your graph down really small. So what I want you to do is I want you to find the smallest value and the biggest value for each axis, and I want you to round the smallest value down and round the biggest value up to something that makes kind of a reasonable starting and ending point for each axis. After you've done that, I want you to take your maximum and subtract your minimum, and then I want you to divide by your number of squares. So that's going to give you kind of where your interval needs to be, how much each square needs to be worth. But if you get something that's kind of funky or a decimal, I want you to round it up to a, quote, sensible interval. 1s, 2s, 5s, 0.5s, 10s, things that are easy to count by. I don't want you, if it comes up with, something really close to 3, I don't want you to use 3, heaven forbid 7. Nobody wants to be counting blocks 3, 6, 9, 12. That's really obnoxious. So let's look at an example. So I just made up some data. Here's my y data, and here's my x data. And for the sake of argument, let's imagine that this graph paper is 30 by 30. Now you can look at that and say, Mr. Edwards, this is not 30 by 30, but we can pretend. And like I said in the previous step, step 1 is to look at your biggest data and your smallest data and round them to something reasonable. No one wants to stop at 166 and no one wants to start at 123 because both of those numbers are sort of in the middle of nowhere. So I'm going to call 166, round that up to 170, and round 123 down to 120. And I'm going to subtract those and divide by my number of squares. That gets me 50 over 30, which equals 1.6 repeating. And that is ugly. No one wants to use 1.6 repeating as an interval. So this is where we use that third step to round it to something. Can't go by ones, we'd run out of room before we got all the way up, so we round it up, always round up, and we'll call that 2. So I would be coming over here, and I would be starting my graph at 120. Now I could number each square, 122, 124, 126, 128, going by 2s, but that might make my axis kind of crowded, so I might count up 5 blocks and just label the next one 130. So my blocks are still worth 2. I'm just labeling every 5 just to keep things kind of clean. And so that first point that's 123 on the y-axis, I'd be plotting it at about right there because it's halfway between 122 and 124. Now let's go back and look at the x data, which is kind of different because it's really small. And there is not a very large difference, but I'm going to do the same steps. I'm going to take my biggest one, 2.47, and I'm just going to call that 2.50. And I'm going to round my first one, 1.03, to just 1. And I'm going to divide that by my number of squares. and that gets me 1.5 divided by 30. That comes out to 0.05. Now that's pretty reasonable. I can count by 0.05. It's just like counting by fives. So I want to go over my first x data would be 1. And again, I don't want to get too crowded here going 1, 1.05. I'm probably going to skip and call my next one 1.1, and then skip and 1.2, and so on until I get all the way out to 2.5. And that's an example of following those steps, and that would make sure that my line plots and probably fills up most of this graph. So we're going to finish up with slope. Maybe you've seen this, maybe you've not, depending on where exactly in your math courses you are. But it's always going to be change in y, y2 minus y1, divided by change in x, x2 over x1. Some people remember rise over run, and that's because the change in y is how much the graph rose, because y is vertical, and the change in x is how much the graph ran sideways, because it's horizontal. I like that. It keeps me straight, y's over x's. And for some statistical reasons that I'm not going to go into, I'm always going to pick my last point and my first point as my x2, y2, and x1, y1. So on our data for y and x, the last point was 166 for y and 2.47 for x. And the first point was 123 for y and 1.03 for x. So I'm just going to plug those into this equation. 166 minus 123 divided by 2.47 minus 1.03. I'm going to stick that in my calculator, and we get 29.86. And that's a kind of a big number for slope, but that makes sense because remember, we had very large changes in y for very small changes in x. So what that means is for every 1 that this graph goes over on the x, it goes up 29.86 units on the y. And that's how to calculate slope, and that's where we're going to finish up with this topic on graph setup and slope.